Alright, let's get our hands dirty and dive into the amazing world of electric vehicles, or EVs. I've built some wild things in my workshop, but the engineering inside these cars is truly something special. An electric vehicle is a machine that moves using electricity instead of gasoline. Think of it less like your old gas guzzler and more like a massive, sophisticated remote control car you can actually drive. There's no engine roaring, no exhaust fumes, and no trips to the gas station. Instead, you plug it in, charge it up, and you're ready to roll. It's a completely different way of thinking about personal transportation, and it's built on some fascinating principles of science and engineering. So, what makes an EV go? It's not magic. It's a collection of brilliant components working together in perfect harmony. We're going to break it down, piece by piece, so you can see exactly how it all works. Forget everything you know about pistons, spark plugs, and oil changes. We're talking about batteries, motors, inverters, and controllers. These are the core building blocks of every single electric car on the road today. Each part has a very specific job, and when they all do their job right, you get that smooth, quiet, and instant acceleration that EVs are famous for. It's a symphony of electrons and engineering. To really understand this stuff, you have to visualize it. Imagine we've taken a brand new EV and sliced it right down the middle like a giant science project. This is what we call a cutaway diagram. You'd see all the major parts laid out with labels pointing to each one. You'd see the big battery pack sitting low in the car's frame, the compact electric motor near the wheels, and all the wires and control units connecting everything. This kind of visual aid is fantastic because it takes the mystery out of the machine. It lets you see where everything is and how it fits into the bigger picture, turning abstract concepts into something tangible. Before we get into the nitty-gritty of each component, let's appreciate the overall design. In a traditional car, the engine is a big, heavy block of metal that dictates much of the car's shape. With an EV, engineers have more freedom. The components are often smaller and can be placed in different spots. This is why many EVs have a front trunk, where the engine used to be. This clever packaging isn't just for show, it often leads to a lower center of gravity, which makes the car handle better. It's a complete rethinking of car design from the ground up, all thanks to electricity. First up is the battery pack, and folks, this is the big one. It's the single most important and heaviest component in any EV. Think of it not as a regular car battery, but as the vehicle's fuel tank. It doesn't hold gasoline. It stores a massive amount of electrical energy. This pack is actually made up of thousands of smaller battery cells, all linked together, much like the individual batteries you put in a flashlight, but way more powerful and rechargeable. These cells are carefully managed by a sophisticated system to ensure they charge and discharge safely and efficiently, giving the car its range, the distance it can travel on a single charge. Next, we have the electric motor. This is the part that creates the motion. It's the muscle of the car. Unlike a gasoline engine with all its complex moving parts, an electric motor is beautifully simple. It works on the principle of electromagnetism, the same force that makes magnets stick to your fridge. When electricity from the battery flows into the motor, it creates magnetic fields that spin a central shaft. This spinning motion is what turns the wheels. The best part? It delivers power instantly. That's why EVs feel so quick and responsive the moment you press the accelerator pedal. There's no waiting for the engine to rev up. Let's compare these two. The battery is like the giant pantry in your kitchen, stocked full of all the food or energy you'll need for the week. The electric motor is like your blender. It doesn't store any energy itself, but when you plug it in and flip the switch, it instantly converts that electrical energy from the wall outlet into powerful spinning motion to make your smoothie. The battery provides the potential, and the motor turns that potential into action. This simple, direct relationship is what makes the electric powertrain so incredibly efficient compared to its gasoline counterpart, which loses a lot of energy to heat and friction. Visually, these two parts are distinct. A diagram would show the battery as a large, flat rectangle that forms the floor of the car. This placement keeps the car's weight low and balanced. The motor, in contrast, would be a much smaller cylindrical unit located near the axle of the wheels it's driving. Labeled arrows could show the flow of electricity from the battery to the motor, and then another set of arrows could illustrate the rotational force being sent from the motor to the wheels. Seeing them in relation to each other makes their roles crystal clear. One stores the power, the other uses it to create movement. Now let's talk about the unsung heroes of the EV. First is the inverter. This component is a crucial translator. You see, the battery stores electricity as direct current or DC. Think of DC as electricity flowing in one steady direction, like water in a straight canal. However, most EV motors run on alternating current, or AC, where the electricity rapidly switches direction back and forth. The inverter's job is to take that steady DC power from the battery and convert it into the AC power that the motor needs to operate. It's the middleman that allows the battery and motor to speak the same language. Then we have the onboard charger. This is the part that lets you refuel your car. When you plug your EV into a charging station or a wall outlet, you're feeding it AC power from the grid. But remember, the battery can only store DC power. So, the onboard charger's job is to take the incoming AC electricity and convert it into DC electricity to be stored in the battery pack. It's essentially doing the opposite job of the inverter. Think of it as a currency exchange for electricity, making sure the power from the wall is in the right format for the battery to accept. The final piece of this electronic puzzle is the controller. If the battery is the heart and the motor is the muscle, the controller is the brain. This is the central computer that manages everything. When you press the accelerator pedal, you're not physically connected to the motor. Instead, you're sending a signal to the controller. The controller then interprets how hard you're pressing the pedal and tells the inverter exactly how much power to pull from the battery and send to the motor. It regulates the speed and torque, manages battery health, and even controls regenerative braking, where the motor acts like a generator to send power back to the battery when you slow down. To make sense of these parts, a flowchart diagram is your best friend. Imagine a box labeled charging port with an arrow pointing to the onboard charger. From there, an arrow points to the battery, showing the flow of energy during charging. For driving, you'd have an arrow going from the battery to the inverter, and then to the motor. The controller would be a central box with dotted lines connecting to the accelerator pedal, the battery, the inverter, and the motor, showing that it's monitoring and managing everything. This visual map shows how these components are not just parts, but a connected system. So, we have power from the battery converted by the inverter and used by the motor to create spin. But how does that spinning motion actually make the car move forward? That's the job of the drivetrain. In an EV, the drivetrain is much simpler than in a gasoline car. It's the collection of components that delivers power from the motor to the wheels. In many EVs, this is just a simple single-speed transmission and a couple of axles. The motor spins, the transmission reduces the rotational speed to a usable level, and the axles turn the wheels. That's it. No complex gears to shift through. This simplicity is a massive advantage. A traditional car has a complicated transmission with multiple gears because a gasoline engine only operates efficiently within a narrow range of speeds. An electric motor, however, is efficient across a huge range of speeds from 0 RPM all the way up to its maximum. Because of this, most EVs don't need a multi-gear transmission. They just need one gear to get the job done. This means fewer moving parts, less maintenance, and that signature smooth, seamless acceleration. You just press the pedal and go with no jerks or pauses for gear changes. To help people visualize the drivetrain, an animation would be perfect. You could show the cylindrical motor starting to spin. Connect it to a small gearbox, the single-speed transmission, where you can see a large gear being turned by a smaller gear, illustrating how the speed is reduced but the torque, or turning force, is increased. From that gearbox, you'd see the axles, long shafts, extending out to the wheels. As the gears in the transmission turn, the axles turn, and finally, the wheels turn, pushing the car forward. This step-by-step animation would make the transfer of power from the motor to the road perfectly clear. In summary, it all comes together like a well-rehearsed team. You press the accelerator, sending a signal to the controller tells the inverter to pull DC power from the battery, the inverter converts it to AC power and sends it to the motor. The motor spins, turning the drivetrain's transmission and axles turn the wheels, and you glide silently down the road. Every part has a job, and they perform it with incredible efficiency. It's a beautiful, elegant system that's simpler, cleaner, and in my opinion, a whole lot cooler than the old way of doing things. And that's no myth.